let's jump into this example. The situation here is Max got a 27 on the ACT, and Sam got a 775 on the SAT Math. And the question is, who did better? 27 on the ACT versus 775 on the SAT Math. Can you just say that 775 is better because it's bigger than 27? Well, no, because these are two different tests that are measured on two different scales. So it doesn't really make sense to compare them directly, right? This is kind of like asking, who's better, Steph Curry or Jared Goff. So for my non-sports fans, who's better? Steph Curry, who's a basketball player, or Jared Goff, who's a quarterback on a football team? It doesn't really make sense to compare them directly, right? Because they're playing different sports. So that's what we're going to talk about on this front page, is how do you compare two things that you can't compare directly. And the way we're going to do it is we're going to use what we talked about in the last lecture, which was the standard deviation and the empirical rule. Okay, so the empirical rule says if you put the mean in the middle, so we'll start with the ACT. The mean for the ACT is 21, so 21 in the middle. And then we're going to use the standard deviation to count upward. Okay, standard deviation for the ACT is 3. So we're going to use 3 to go up 3 times and then also down 3 times. So 21 plus 3 is 24. Plus 3 again is 27. Plus 3 one more time is 30. And then going downward, 21 minus 3 is 18. Minus 3 again is 15. And then minus 3 one more time, 12. And then we're going to do the same thing for the SAT Math. The mean for the SAT Math is 514. The standard deviation is 87, so we'll use that to go up 3 times and then down 3 times. So 514 plus 87 is 601. Plus 87 again, 688. Plus 87 one more time, 775. And then going the other way, 514 minus 87, 427. Minus 87 again, 340. And then minus 87 one last time. $253. Okay. Now, what the empirical rule says is, even though, right, these are scores on the SAT and these are scores on the ACT, which we said were two things that we can't compare directly, what the empirical rule says is, what the empirical rule is doing is, it's putting these two situations on the same picture, which will have the same percentages. And the percentages which I'm talking about are the 68, 95, 99.7. So between 1 up, 1 down is 68% of your data. Between 2 up, 2 down is 95% of your data. And then between 3 up, 3 down is 99.7% of your data. And then everything is 100%. Okay, and it's going to be the same numbers and percentages on this picture, which I won't draw, but it's the same thing. So same numbers on the right picture also. Okay, so now that we have the two situations on the same picture, we can now compare. So which one is better, 27 or 775? And why? Here's 27. And here's 775. So which is better? Notice that 27 is 2 steps above the mean, and 775 is 1 step, 2 step, 3 steps above. So is it true that 775 is going to be better because it's 3 steps above versus 2 steps above? And the answer is yes. 775 is going to be better for that reason. And even more, in the last lecture, we also talked about how to find even more percentages beyond these, right? So let's find the percentage that is to the left of 27. And the way I'm going to do it is I'm going to go from 27 to the middle, and then from the middle all the way to the left. Okay, middle all the way to the left should be half of 100%, which is 50%. 27 to the middle should be half of 95%. So half of 95 is 47.5. Okay, so together, this is 97.5%. Let's do the same thing for the 775. So what percent is to the left of 775? So we'll go from 775 to the middle, and then from the middle all the way to the left. Okay, middle all the way to the left. Middle all the way to the left, we said was 100%. I mean, half of 100%, which is 50%. 775 to the middle. That's 3 steps to the middle, 3 steps above to the middle, which should be 3 steps above to the middle, should be half of 99.7%. Okay, so half of 99.7, so 99.7 divided by 2, 49.85%. Together, that's 99.85%. Okay, so what this is telling me is that Sam, who got a 775, his score is higher than 99.85% of the population who took the test. Max, who got a 27, his score is higher than 97.5% of the population who took the test. In other words, Max did better, or Max beat 97.5% of the people who took the test. Sam beat 99.85% of the people who took the test. So in other words, Sam did better because he beat more people than Max. And that's why Sam's score is better. Okay? Now, let's take a look at this next example. What about 28 on the ACT versus 710 on the SAT Math? What's different here? How does 28 and 710 differ from 27 and 775? Well, 27 and 775, these are special because they fell directly on one of these steps. Okay, 775 was exactly 3 steps above. 27 was 2 steps above. 28 and 710 don't fall on one of those steps. Okay, so what do? Well, you do what's called a z-score. So let me tell you the formula, and then we'll talk about it. All right, so we've seen some of these symbols before. The X here is your data. This symbol, that's mu, it stands for mean. At the bottom, this is sigma. We've seen this before in the last lecture. This is the standard deviation. Okay, so let's calculate the z-score for the ACT and then the z-score for the the SAT math, the 710. So let's start with the 28. Okay, so first your data, which is the 28, minus the mean. So this, we're talking about the mean for the ACT. The mean for the ACT is 21. So 28 minus 21. And then over standard deviation for the ACT. Standard deviation is 3. Okay, so we'll calculate that a little bit later. And then for the SAT, uh, 710 is our data for the SAT. Minus the mean for the SAT was 514. Standard deviation for the SAT, standard deviation was 87. Okay, so let's calculate these on a calculator. 28 minus 21 over 3. Rounded to 3 decimal places is 2.333. Okay, so if you're using the decimal scientific calculator, just type it in exactly like that. So 28 minus 21 on top, 3 on the bottom. If you're using another calculator, then you should probably do 28 minus 21 equals, and then divide by 3. So 28 minus 21 is 7, and then 7 divided by 3 is this answer. So for the SAT, 710 minus 514 over 87. Rounded to 3 decimal places, that's 2.253. Okay, what does this thing mean? Well, 28, we said wasn't exactly on one of those steps, right? It's actually between, that's 1 step, 2 steps. 28 is somewhere there, and then that's 3 steps. So 28 is somewhere between 2 steps and 3 steps above the mean. What we just calculated is we're saying that it's exactly 2.333 steps above the mean. Okay, so the z-score tells you exactly how many steps you are above or below the mean. Okay, and let me be more specific here. When I say steps, it's how many standard deviations above or below the mean. And then similarly, the 710. 710 is, that's 1 step, 2 steps. 710 is somewhere between 2 steps and 3 steps. But we're saying here that it's exactly 2.253 steps, or 2.253 standard deviations above the mean. So these two pictures are the same. We're saying what we just calculated. We're saying that the 28 is actually slightly more to the right than the 710, right? So if you're slightly more to the right, you beat slightly more people than 710, which means the 28 is going to be better, right? Because it's slightly more to the right than the 2.253. So the ACT is better. Okay, so this idea of what percent is below, what percent is to the left of you, or what percent of the population do you beat? So that idea is actually called a percentile rank. We see percentile rank mentioned a lot in standardized test scores, right? And the percentile rank tells you what percent of the population is below you. In other words, what percent of the population scored less than you, which is the same thing as saying what percent of the population did you beat. Another situation where you see percentile rank is in the doctor's office. Here's a growth chart. So this is a growth chart for baby girls from birth to 36 months. So how do you read this, this growth chart? At the bottom here, you have age in months. And then on the side here is the weight of the baby. Okay, so say I have a baby girl who is 15 months and 24 pounds. Right, so you're gonna see where this meets. It meets right here. And then look at the curve that it lands on. So it landed on this curve, which is 75. That's the percentile of that baby. So what does this percentile mean? It means that 75% of the population is below that baby. In other words, 75% of the population weigh less than that baby. Or another way to say it is, if you have a 15-month baby girl who is 24 pounds, then that baby is heavier than 75% of all the babies at that age. So how do you calculate the percentile? I have two boxes here. The box on the left is the procedure for computing the data value corresponding to a given percentile. So left box is when you're given a percentile, and you want to find the data value. Okay, box on the right is procedure for computing the percentile corresponding to a given data value. So this is when you're given a data value, and you want to find the percentile. Let's take a look at example 1. Following is a list of the number of hazardous waste sites in several U.S. states. Okay, this is the data. Part A says find the 25th percentile. Which box do you use? Are you given the percentile or are you given the data value? 25th percentile. Okay, you're given the percentile. 25, right, is not a data value because if you look at data, 25 is nowhere in the data value, right? So 25th percentile is a percentile. So we're given the percentile and we're asked to find a data value, right? Which means we're using the left box. So left box says step 1, arrange the data in increasing order. If I look at my data, it's already in increasing order, so we're good there. So step 1 is done. Step 2, let n be the number of data values in the data set. For the p percentile, compute the value L equals this. So let's compute that. So we're going to go L equals, it's p over 100. P is the p percentile. In our case, it's the 25th percentile. So it's going to be 25 over 100 times n. N is the number of values in the data set. So how many data values do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 in each row. So that's 10, 20, 30, 40, 41, 42, 43, 44. So there's 44 data values total. And then we'll compute that. So 25 over 100 times 44. It's 11. Okay, we're not done because all we did was step 2. Step 3 says if L is a whole number, do this. If L is not a whole number, do this. L here is 11, so that's a whole number. So we're doing the first part here. If L is a whole number, then the p percentile is the average of the number in position L and the number in position L plus 1. So I want the average of the number in position 11 and the number in position 11 plus 1, which is 12. So what I want here is to find the number that's in position 11. So count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 24. And a number in position 12, which is the next one, 27. and I want to average that. So add them up and divide by 2. Okay, 24 plus 27 divided by 2 is 25.5. And what does this mean? Percentile, once again, is the percent that's below you. Okay, so what this is saying is that 25% of the data, I would say approximately 25% of the data is below this number. And that's what the percentile means. Part B, find the 62nd percentile. Okay, once again, are you given the percentile or are you given the data value? So are you given the percentile or are you given one of these numbers in the data set? This is a percentile. Okay, so we're doing the left box again. Step 1 is done, put the data in increasing order. Step 2, find the L. All right, so we'll do the L. It's P over 100. P is our percentile. In our case, it's 62. So it's 62 over 100 times N. N is the number of data values. We counted already. It's 44. So 62 over 100 times 44. 27.28. Okay, we're not done. All we did was step 2. Okay, step 3. If L is a whole number, do this. If L is not a whole number, do this. L is not a whole number. Okay, so we're going to do this bottom part. So if L is not a whole number, round it up to the next higher whole number. So we're always going to round it up. So if L is not a whole number, we're always going to round it up. Okay, so even though it's 0.28, you're still going to round it up to 28. And then we're not done yet because, so we rounded it up. The P percentile is the number in position corresponding to the rounded up value. So I want the number in position 28. Okay, so what number is in position 28? Okay, there's 10 in each row, so that's 10, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so 36 is in position 28. And then the interpretation, the percentile tells you what percent of the data is below. So we're saying that approximately 62% of the data is below this number, 36. Okay. Common mistakes I see a lot here is people will find L, find 11, and then they stop. Okay, or they'll find 27.28, they round it up to 28, and then they stop. So don't stop, right? So that's just step 2. Think of L as the location, right? So the L part is just telling you what location, and then you actually have to go to your data and look for that location, and then find your final answer. Okay, so before I move on, let me connect this with something we talked about already. So we talked about the median, right? And we said the median was the middle number. And it's the middle number in the sense that half of the data is above and half of the data is below. Okay, so this is really just a percentile, right? Half of the data is below means that 50% of the data is below, which is the same thing as saying that it's the 50th percentile. Okay? So the median is really just the 50th percentile. And it also explains why we have kind of two different situations here, right? So in part A, we found two numbers and then we averaged them. Whereas in part B, you only look for one number, okay? And that's the same reason why when we looked at median, right, sometimes there is a number in the middle, and sometimes you have to average two numbers in the middle. And that's the two situations we have here. So sometimes you have to average two numbers, and sometimes there is just a single number. Part C. The state of Texas has 34 hazardous waste sites. What percentile is this? Write a sentence interpreting your answer. Okay, question is, am I using the left box or the right box? I'm giving you 34, and 34 is a hazardous waste site, which means 34 is actually one of my data values. Right, it's actually right here. So I am giving you a data value, which means we'll be doing the box on the right. So step 1 says arrange the data in increasing order. I think we're good. The data is in increasing order. Step 2, let X be the data value whose percentile is to be computed. Use the following formula to compute the percentile. So let me write down the formula. The formula says percentile equals and it says 100 times on top, number of values less than X. Okay, in our case, our data value is 34. So we're looking for number of values less than 34. So how many data values is less than 34? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So there's 23 numbers that are less than 34. So 23. There's also a plus 0.5. And on the bottom, number of values in a data set. Okay, so how many data values are in the entire data set? And I think we counted, we said it was 44. All right, so let's compute this. So it's 100 times fraction up top, 23 plus 0.5, on the bottom, 44. Round this to 3 decimal places, this is 53.409. Okay, let's check if we're done. At the bottom, it says round the result to the nearest whole number, right? So we're gonna round this to the nearest whole number. Nearest whole number just means round regularly, okay, so to a whole number. That's 0.4, so we should round down to 53. So our final answer here is 53 is our percentile, so that's 53rd percentile. And then the interpretation. The percentile tells you what percent is below your data value. So this is approximately 53%. Approximately 53% of the data is below the data value. The data value here is 34. And that's how you compute the percentile. Now, let me talk a little bit about the formula. So the percentile is what percent is below. Okay, so the 23 makes sense. So if I want to know what percent is below 34, I should actually count how many is below 34. And that's what the 23 is. Okay, if the 0.5 wasn't there, I think the formula would make sense. Okay, so we're counting how many is below. We're dividing it by the total, right? And then we multiply by 100. So multiplying by 100 just converts it to a percent. The question is, where does this 0.5 come from? And that 0.5 comes from people not agreeing. So when we say we're counting how many is below 34, question is, should you include 34 or should you not include 34? So when I counted, right, notice I didn't include 34, right? I started with the 33 and I counted. So I don't include the 34, okay? And that's the way that we're gonna do it in this class. But not everybody agrees on that. So some people, some statisticians will say include 34, and some will say don't include 34. So the 0.5 is the compromise, right? So we're going to add 0.5 to kind of meet in the middle and compromise. And that's where the 0.5 comes from. Okay, next up is quartiles. So quartiles sounds like quarter. So a quarter is 25 cents. First quartile is just the 25th percentile. Second quartile, 2 quarters, is 50 cents. So the second quartile is the 50th percentile. And remember, we said the 50th percentile is really just another name for the median. Okay, so 50th percentile is really just the median. Third quartile, that's 3 quarters, that's 75 cents. So that's 75th percentile. The interquartile range, this is just Q3 minus Q1. Lower outlier boundary, this is Q1 minus 1.5 IQR. So you start with the lower quartile, which is Q1, and then you go down by 1.5 IQR. Upper outlier boundary, you start with the upper quartile, which is the Q3, and you go up by 1.5 IQR. Let's now compute all of those quantities that we talked about on the previous page using the data from example 1. Okay, so Q1, Q2, Q3, these are the quarters. So Q1 is just the 25th percentile. Q2 is the 50th percentile. Q3 is the 75th percentile. So I'm giving you the percentile, which means what you're really doing is just the left box for all 3 of those. Okay, the 25th percentile, lucky for us, we did already in part A, right? We found the 25th percentile, and we found that it was 25.5. So part A, Q1 is done. It's 25.5. And this was from example 1. Part A. Q2, the 50th percentile, we didn't do yet, so we actually have to do it. So step 1, arrange the data in order. We're good. Step 2, compute this L. Okay, so L equals, and it's going to be the percentile you want over 100, which is 50 over 100, times the number of data values in the data set. So the number of values in the data set, I think we've counted already. It's 44. So 50 over 100 times 44. 22. So remember, we're not done. That's just the location that we want. So we just did step 2. Step 3, if L is a whole number, this is what you're supposed to do. If L is not a whole number, this is what you're supposed to do. In our case, L is a whole number, right? So we're supposed to average the number in position L and a number in position L plus 1. So we're going to average the number in position 22 with the number in position 23. So I'm going to look for the number in position 22. I think we said that there was 10 in each row, so that's 10, 20, 21, 22. So it's 31. And then the number in position 23 next to it is 33. Right, so we're going to average these two numbers. So 31 plus 33 over 2. Is 32. That's Q2. Q3, the 75th percentile, we're going to start off the same, find the L. Percentile I want, so 75 over 100, times the number of data values in a data set. It should be the same thing, since we're talking about the same data set here. So 75 over 100 times 44. This is 33. Okay, that's just step 2 of the process. Step 3 is if L is a whole number, do this. If L is not a whole number, do this. L is a whole number here, so we're going to average the number in position L and the number in position L plus 1. So here, I'm going to look for a number in position 33 and a number in position 34. And I'm going to average those two numbers. So number in position 33, that's 10, 20, 30, 31, 32, 33, that's 38. And a number in position 34 is 31, 32, 33, 34, 42. And we're going to average those. So add them up, divide by 2. All right, so 38 plus 42 on top over 2. It's 40. And that's Q3. IQR, the interquartile range, is you take your Q3 and minus your Q1. So it's Q3 minus Q1. So Q3 is here is 40 minus Q1, 25.5. And that is 40 minus 25.5, 14.5. Okay, lower outlier boundary. So lower outlier boundary, you start with your lower quartile, which is Q1. And then you subtract 1.5 IQR. So in our case, Q1 is 25.5 minus 1.5 times the IQR, which was the 14.5. Okay, so 25.5 minus 1.5 times 14.5, 3.75. Upper outlier boundary, start with your upper quartile, which is the Q3, and then plus 1.5 IQR. Okay, notice that one of them is minus, the lower one you subtract, and then the upper one you add. Q3, here it was the 40, plus 1.5, IQR was 14.5. So 40 plus 1.5 times 14.5, 61.75. Part G, list the outliers. So the outliers are just data values that are like way big or way small compared to most of the rest of your data. So the lower outlier boundary and the upper outlier boundary help you identify what's considered an outlier. So any number, any data value that's below 3.75 is considered an outlier. Any data value that's above 61.75 is also considered an outlier. So let's look at our data. Do I have any data values that's less than 3.75? Yes, 0, right? So 0 is less than 3.75. So 0 is considered an outlier. And I think that's it for the less than 3.75. Any data value that's above 61.75 is also considered an outlier. So do I have any data values that's above 61.75? Yes, I have a whole bunch. I have 67, 86, 97, 97, and 116. So all of those are outliers also. 67, 86, I have two 97s. You can list them twice or you can list it just once. That's up to you. I'll list it twice, and then 116. All of those are considered outliers. So these are numbers that are way big or way small compared to the rest of your data. The 5-number summary is going to be the minimum, Q1, Q2, Q3, and the maximum. Now remember, Q2 is the 50th percentile, which is just the same thing as the median. And the 5-number summary for the data from example 1. Here's the data from example 1. The minimum here is 0. The maximum is 116. And then Q1, Q2, Q3, we found on the previous page. Q1 was 25.5, Q2 was 32, Q3 was 40. So 25.5, 32, and 40. And that's the 5-number summary for the data in example 1. Now, the graph that goes with the 5-number summary is called a box plot. Okay, so let's draw a box plot. Let me first draw my x-axis. Okay, so for my x-axis, I need to go from 0 all the way up to the max. So 0 all the way up to 116. I think I'll count by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. And then let me label what the x-axis means. So our data, what do my data values mean? My data values are the number of hazardous waste sites. Okay, so these numbers here represent the number of hazardous waste sites. And now let's draw my box plot. So the box part comes from Q1, Q2, and Q3. Okay, so I'm going to draw a box using Q1, Q2, and Q3. So Q1, 25.5 is somewhere here. Q2, 32 is somewhere here. Q3, 40 is right here. Okay, and that's Q1, Q2, and Q3. And I'm going to make a box out of this. Okay, that's the box part. Q1, Q2, Q3. Sometimes box plots are called box and whisker plots because we're going to draw whiskers that come out of the box. Now the whiskers come from looking at the lower outlier boundary and the upper outlier boundary, right? The 3.75 and the 61.75. So 3.75 is between the 0 and the 5. Okay, 61.75 is between the 55 and 67. So the lower, you're going to go up to the next data value. So you're going to go up to the 5. The upper, you're going to go down to the next data value. So you're going to go down to 55. So my whiskers will go to 5 on the low end and 55 on the high end. Okay, so on low end, it's going to go to 5, which is right here. Upper end, we set to 55. Okay, so once again, use your lower outlier boundary and your upper outlier boundary. My lower outlier boundary was 3.75, which is between the 0 and the 5. My upper outlier boundary was 61.75, which is between the 55 and 67. And then you're going to go in. So the upper, you're going to go down. The lower, you're going to go up. And then to the next data value. And then those two numbers are where you draw your whiskers to. Okay, so 5 on the low side and then 55 on the high side. And then the very last thing we're going to do is we're going to put the outliers on the picture. Okay, so there should be an outlier at 0, and we're going to label it with X's. So that's an outlier at 0, and then I have outliers at 67, 86, 67, 86, 297s. You can list them twice, or you can just do it once, and then 116. And that's a box plot. Okay. Determine the shape of the data from the box plot. So when I say shape, I mean skewed left, skewed right, or symmetric. So when we talked about histograms, remember, skewed left means that the tail is on the left side, skewed right means the tail is on the right side, and then that's symmetric. So on a box plot, you can read the box if you want, but let me just tell you. Go to the center of the box, all the way to the right, versus center of the box all the way to the left. Okay, whichever side is longer is the direction of the skew, right? So this one, obviously, right side is longer, so this is skewed right. Okay, middle of the box all the way to the right, middle of the box all the way to the left. Okay, whichever side is longer, that's the direction of the skew. So this one, obviously, left side is longer, so this is skewed left. This picture, middle all the way to the right, middle all the way to the left. This one's about the same on both sides, so this one would be symmetric. All right, so looking at my box plot here, is this skewed right, skewed left, or symmetric? So middle, all the way to the right. So when I say all the way to the right, you want to include the outliers also. So middle all the way to the right versus middle all the way to the left. So obviously, right side is longer. Okay, so this is obviously skewed right. Once again, middle all the way to the right, and when I say all the way to the right, include the outliers also, and then middle all the way to the left. Whichever side's longer is the direction of the skew. Now that you know how to make a box plot, can you go backwards? If I give you a box plot, can you read it? So example 3 says the ages of a sample of trees in a park are summarized in the box plot below. There it is. Find the following quantities: the minimum, maximum, median, and 75th percentile. Minimum is pretty easy. It's the smallest number. It's 5. Maximum, biggest number, 98. Okay, median and 75th percentile. So let's remember how a box plot works. The box part is made up of Q1, Q2, and Q3. Okay, and Q1, Q2, and Q3, Q1 is just the 25th percentile, Q2 is the 50th percentile, and Q3 is the 75th percentile. The 50th percentile is just another name for the median, right? Because the 50th percentile means that 50% or half of your data is below it. So that's just what the median means. And then to answer this, the median is just 66. 75th percentile is Q3, which is 74. Part B. What percent of the trees is below the age of 66? The box plot breaks up your data into 25%, into quarters. So from Q1 to Q2, that's 25% of your data. From Q2 to Q3 is another 25% of your data. Okay, right side of the box all the way to the right side is another 25%. Left side of the box all the way to the left side is another 25%. Okay, so remember when you're doing this, include the outliers also. Don't just throw those away. Okay, so left side all the way to left is 25%. Q1 to Q2 25%. Q2 to Q3 25%. Right side of the box all the way to the right is 25%. What percent is below 66? So here's 66. Below would be 25% plus 25%. So 50% is below. The youngest 25% of the trees is between what two ages? So youngest meaning the lowest 25%, right? The lowest 25%. The lowest 25% is this, which is between 5 and 57. Okay, so once again, don't throw away the outliers, right? So don't get tricked and say 32 and 57. It's actually 5 to 57. And then part D. Do you expect the mean to be greater than, less than, or approximately equal to the median? Okay, so this is going to have to do with the skewness. Middle all the way to the right versus middle all the way to the left. Whichever side is longer is the direction of the skew. So middle all the way to the right, middle all the way to the left. Left side is definitely longer, so this is skewed left. But that doesn't really answer our question, right? Because what does skewed left mean? Remember when we talked about skewedness and the mean and the median, we said that if it was skewed left, then the mean is to the left of the median. If it's skewed right, then the mean is to the right of the median. So this is skewed left. So the mean is to the left of the median. But what does that mean? So being to the left means what? Is that less than, greater than, or equal? So being to the left means that you're less than, right? So the mean will be less than the median. Example 4. According to the National Center for Health Statistics, the median height for 20-year-old males is 69.5 inches. The 10th percentile is 66 inches, and the 95th percentile is 74 inches. Part A. What percent of 20-year-old males have height less than 66? Okay, let me actually put these numbers onto a picture so that it's easier for me to understand. I'm going to put all the heights. So this 69.5, 66, and this 74. So it's going to be 66 first, 69.5, and the 74. Okay, what do these numbers mean? The 69.5 is the median. What does that mean? It means that 50% of the data is below it, right? So the 69.5 has 50% to the left of it. Okay, that's what the word median means, is the 50th percentile, which means that half your data is below it. The 10th percentile is the 66, which means 10% of the data is below 66. So 10% is to the left of 66. The 74 is the 95th percentile, which means 95% of the data is below 74. Okay, so on my picture, 95% should be to the left of 74. And I think we can answer all the questions just by staring at this picture. Part A, what percent is less than 66? Here's 66. So this is really just asking what percent is to the left of 66. 10%. That was pretty easy. Part B, what percent is greater than 74? Here's 74. Greater than, I went to the right of 74. If I know it's 95% to the left, what percent is to the right? 5%. Okay, so all we're doing here is I know it's 95% to the left, which means I know the rest of it, which is 100% minus 95%. Is to the right. Okay, so anytime you want the other side, just do 100 minus that number. Part C, what percent is between 66 and 69.5? I know 69.5 all the way to the left is 50%, and I know 66 all the way to the left is 10%. If I take this and subtract this, that should give me this, which is exactly what I want. So 50% minus 10% gives me between 66 and 69.5. So 50% minus 10%. That's 40%. Part D, what percent is between 66 and 74? Same idea, right? I know this is 95%. I know this is 10%. So 95%, if I just subtract 10%, that should give me exactly that piece, which is 66 to 74. So this is going to be 95% minus 10%. And that's 85%. Okay, that's all I have for you today. Have a good day. Talk to you later.